Okay, so let's start investigating ADC in Atmega 128. It has got an 8 multiplex single-ended input channels and 7 differential input channels. I'll show you the architecture in a minute. 2 differential input channels with 10 times or 200 times gains. 0 VCC input voltage range and 3 sources of voltage reference, internal selectable 256 VREF generator. It has got a 10-bit resolution, so the discrete one was 8-bit, so this has got a higher resolution compared to the discrete one. Um, 0.1 less significant bit integral nonlinearity and plus or minus 2 less significant bit absolute accuracy. So 13 to 260 microsecond conversion time. It has got a free running mode and the single conversion modes. Interrupts can also be used, and there's a noise canceller, conversion and interrupt during the sleep mode, and we have got 76.9 kilosamples per second, 15 kilosamples per second at maximum resolutions. Now, at Mega, this is the architecture of the ADC. We are having the channels over here, ADC channels in the port F, and the band gap reference is over here, internal reference if you want to generate the internal VREF, AVCC, and AREF is also there. So we have got multiplexers which we can use to configure if you want to use differential or single-ended channels. In our cases, in our course, we are just going to use single-ended channels, not the differential ones. If you want to have the gain versions, you can use this amplifier to have it boosted. So in this multiplexer, you can actually choose if you want to have single-ended or differential selections. And it's a 10-bit ADC, so sample and hold comparator is here, conversion logic is here. We have got the prescalers, the max decoder, the data register that it holds the data for after the conversion. And we also have the control and status register, which is ADC SRA. We are going to see the details of each of these registers. But before we move on, we have to make sure that we understand how the power and the signal delivery works in AVR. These analog signals, as we already mentioned, they are quite, let's say, small signals, and we need to have some signal conditioning. And of course, as they are analog and we are actually having some noise in these signals, we have to be really careful. So as they have got already noise, and if we add more noise because of the digital circuitry around it, that will also cause a problem. So in order to keep the digital noise out of the ADC circuitry, it has got its own power supply pin, which is AVCC. So AVCC pin is actually having an extra filter circuitry, which isolates this noise so you can use it more accurately. And ARF typically has a decoupling capacitor, which is around 14 picofarad. And it can also be used as a reference voltage to the analog to digital conversion, as we already mentioned. Now, this noise circuitry actually keeps analog signal path short and reference to a ground plane. And source impedance connected to ADCN should be less than or equal to 10 kilo ohm for sampling time to be negligible. And we can use a noise canceller and avoid driving digital outputs like port F when ADC is on. So we can just reverse port F for ADC, and we don't use it for anything else if we are using analog to digital conversion. And signal components higher than the F/2 should be filtered from the input analog signals. That's also can be taken care. Now, the noise canceller, so we have got a special option in the AVR that we can have a noise canceller. We can power down the CPU So we can actually reduce the digital noise in the chip. In the microcontroller control registers, there's a power management, so we can actually use a sleep mode. So it will make the CPU to enter the noise reduction mode. So it will stop the CPU, I/O clocks, and the memory blocks. If you're not using them, they're just sleeping. In order to use it, we have to enable the ADC, the single conversion mode, and interrupts on. And the CPU just going to wake up whenever the interrupts are coming in, the conversion is completed or so on. And in order to enter the noise reduction mode, we have to set some pins in the microcontroller control register, SM2 down to 0 to 001. And whenever the conversion is done, interrupt just wakes up the CPU so that you can do some other stuff with it. And other interrupts can also wake up the CPU. So we have to be what we can do is while the ADC is working, we can just not accept any of the other interrupts. So one important thing, the ADC clock itself, because successive approximation is actually requires an input clock, and clock is derived from internal CPU clock. There are 7-bit scalar provides outputs as clock divided by 2, 4, 8, 16, 32, 64, and 128, giving a good configuration. Generally, the required clock speed is between 50 kilohertz to 200 kilohertz, depending on the resolution. Now, normal conversion takes 13 clock cycles, but the first conversion, it takes 25 clock cycles because analog circuit needs initialization, so it takes more clock cycles. But the rest are all just 13 clock cycles. And generally, when we have got a 10 megahertz or 16 megahertz clock, and as ADC requires a separate running mode or the clock itself, we generally use a 128 prescaler, which gives around 125 kilohertz at 16 megahertz. And we can actually have a 13 cycle conversion, ordinary, and that will give us with the 16 megahertz around 104 microseconds per conversions. Okay, so depending on the clock that you are using, that might change, but we generally use 128 prescaler in order to have a frequency between 50 to 200 kilohertz. So the multiplexer over here and the 3 pins in the ADCS array. It's the register that we use over here for this mode. And the last 3 bits, least significant bits, are actually the prescaler select bits, and we use them to determine the prescale values. And important one, once again, ADC requires an input clock less than 200 kilohertz for the maximum accuracy. Okay, be careful with that. So we also have some other bits over here, like ADEN bit 7 is the ADC enable, and we also have the ADCS, which is the start conversion. ADFR is the free running mode, and ADIF is the interrupt flag. So it is set when ADC conversion completes and the data registers are updated. ADAR, if you want to enable the interrupt, you have to enable this pin. And the others are the pre-scaling pins. So the free single or multiple runs, what we do with the ADC first, in the ADCS array register, we have to enable the ADC that we are going to use ADC. Then we can choose if it's going to be a single conversion or free running mode. Generally, we configure it in the single conversion in this case, because in order to have a single conversion, you just write 1 to the ADCS, which starts the conversion, and it's gonna be 1 until the conversion is done. And when it is done, it just stops, and the flag is cleared. And if a different channel is selected during the conversion, the current channel finishes the conversion first. So upon completion, the ADIF bit in the ADSR is set. So you can either check by polling, or you can use an interrupt in order to clear it. And the free running mode, similar. You just need to set the free running mode rather than the single mode. First conversion started by writing logic again to ADC-SC, and then it just conversion continues no matter what the ADC interrupt is generated or not, and ADIF is cleared or not. So, and it's not going to clear the ADSC, so it's just a free running. And normally the first conversion takes longer than the rest of it. So ADC multiplexer is quite important because we actually select, it's a select register, so the AD max, we need to be careful. Now, AD max has got some pins like refs are actually used for the reference voltage if you are going to use internal or external one, or internal 2.56 voltage reference. So these are the some reference voltages that we can select. We also have max 4 down to 0. So this is actually helping us to choose the channel. If you are going to use analog channels with single-ended inputs, we can use ADC 0 to 7 with the address the max configuration to 000 to 00111. Or if you want to have differential ones, you can have a different configurations, which goes up to 111. So these are all can be configured with the ADMAX. And there's also ADLAR bit, which I will talk about that as well. So about the refs, if you want to connect the VREF into an external fixed voltage, you will not be able to use the other reference voltage options in the application, as they will be shorted with the external voltage. And also, if we connect a 100 nanofarad external capacitor between the VREF pin and the ground, it will increase the precision and stability of the analog to digital converter, especially when you want to use internal 2.56 volts. So, or if you choose a 2.56 volt as a VRF, the step size of ADC will be 2.56 divided by 124. Maybe I can write that over here. 2.56 divided by 124, because that's giving us the 10-bit resolution. So that is actually 10 over 4, which will be 2.5 milliwatts. And this will reduce the calculations in the software if we are using this mode. Now, ADLAR, which I already mentioned, but I didn't get the details. So we have got two registers to store the ADC converted data, and ADCH and ADCL. Now, these two registers can store the converted data, but ADC is giving 10-bit output, so 6 bits are actually unused. So when you consider a 16-bit register, let's say, you can actually decide which side you are going to have the unused bits. So the first 6 bits or the least significant 6 bits. So you can actually left adjust the results by setting the ADLIR configuration. So if you draw it, ADCH, let's say we have got D9 down to D2, and then so 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the rest will be unused. So D1, D0. And this is where ADLAR is equals 1, so left adjusted. And if ADLAR is equals 0, then what will happen? We have the register, so we have got unused. So we have got D9 and D8, and then D7 to D0. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so this is where it's right justified. Okay, we can actually choose which way you want to write it because you are actually going to read it according to that. So the channel and the gain selection with the max inputs. So we can select the gain for the differential and also selects which combination of analog inputs are going to be connected to the ADC. We can use the ADC input channel source to select either a single or a differential ones. And if you select a single-ended one, you can choose ADC 0 to 7, as I mentioned, and the rest for the differential ones. So these are the configuration bits. And ATmega 128 is designed to support MOSFETs, measure the internal circuits offsets as well. And you can find these configurations based on these differential modes and so on. Right, so result reporting, as I already mentioned, ADLAR 0 and 1, left justified and right justified. So how do we get the results? So when this one is set, the data register ADCH and ADCL, so it's like a 16-bit. When ADCL is read, ADC data register is not updated until ADCH is read as well. And you can just left justify and read only the ADCH and throw away 2 bits of precision. That's also possible. So for single-ended conversion, ADC is Vin times 124 divided by Vref. If we have a differential one, which is not in this course, we positive and negative gain multiplied by 512. And you can see how we can store these data. So how do we set up ATmega 128? Setup involves we have to choose the reference voltage. We generally use AVCC. Select input channel, so which channel you have connected your sensor. Enable interrupts, so rather than waiting for the polling and checking the flag, you can just enable it and shut down all the CPU if it's necessary. And we have to enable the analog to digital conversion. So with reference voltages, which determines the input voltage, maximum input voltage that should be applied, and the smallest voltage that can be resolved. So we use AVCC 5 volts for the ADC reference generally. Should not exceed 5 volts because of the electrical and the software reasons. So that means input voltage resolution is 5 over 124, 4.88 millivolts. and 0 volt gives ADC as 0, and 5 volt gives as hex 3FF. And that's how we can consider it. So how do we program ADC in ATmega 128? So first of all, we have to make the pin for the selected ADC channel an input pin. So turn on the ADC module, so it is disabled upon power on. So we have to set the ADEN bit in ADC SRA. Then we have to select the conversion speed, so the clock, depending on the CPU clock actually. Select voltage references and ADC input channels using the max configurations in the AD max. We have to start conversion by ADSC. Wait for the conversion to be completed either by polling or by the ADF interrupt flag. It's better to use that one. And after the flag is set, that means interrupt, or we have to read the data register low and high to get the digital data output. And if you would like to read another channel, if you like to read the same channel, you can repeat this step. But if you would like to read another channel, or you want to change the ref, then you have to go to the max configuration and you have to change which channel you want to read. Okay, so let's see the first example. Let's see how we can use to configure AVR at Mega 128 with a specific sensor so that we can do some operations and write the code for it. Right, so LM34 produces a voltage output that is linearly proportional to the temperature with the 10 millivolts per Fahrenheit relationship. The range is minus 50 Fahrenheit to 300 Fahrenheit. Determine the VREF to be used for analog to digital conversion. B. Write an assembly program to sense the temperature using polling and output the digital value using port D. And C is write a C program for the same using the crystal frequency 16 megahertz. Now, if we think about with the A, it says determine the VREF to be used. Now, if we use all 10 bits, okay, in order to decide that, this is actually give us a range as 124 times the voltage that we are having is 10 millivolts. So this is 10.24 volts. Now this is outside the sensor range. So it cannot handle that one. And analog to digital range with any of the Atmega VREF options, so we cannot use it at all. If we consider 9 bits, then this is going to be 512 times 10 millivolts, and this is 5.12, still out of the range. And if we use 8 bits, then this is going to be 256 times 10 millivolts, which will be 2.56 volts. Now this is actually in the range, and this is smaller than the VCC, and in this case, internal VRF, which is also 256, is a good option. Okay, so based on the resolution that we have got, we can easily find out the relationship between the sensor and the analog to digital converter range. So we'll use VREF. That's part A, actually. And part B, write an assembly program to sense the temperature using polling and output the digital value using port D. Okay, so we are going to use polling and we have to sense this sensor. We just need to decide where do we need to connect it and how are we going to use it. So let's say B over here. Now, one thing that we need to make sure that it's going to be the port F. Has to be an input port for ADC. Okay, we can connect it to the any channel over there, and it says output the digital value on port D. So port D and output port. Okay, so we are okay with the port D and F. Then we have to, in ADC SRA register, if I go back to the register so that we can see what we need to configure. Now we have to do a single conversion and free running mode. So ADC SRA control register. Now 8 bits, we have to enable it. 2, 3, 4, 5, 6, 7, 8. 8 bit has to be enabled. And we have to use polling, so it's not going to enable the interrupts. Free running mode is 0. Interrupt flag, interrupt enable is 0. We have to think about the pre-scaling. Now, as we already seen that it's 16 megahertz clock, and we have to run the ADC between 50 kilohertz to 200 kilohertz, which we already mentioned here. Okay. So in order to do that, 16 megahertz clock has to be divided by 128, which is going to be 111 as a configuration. Okay, so in this case, ADC SRA register is going to be set as 0 hex 8, because this is 8, and this part will be 7. ADC SRA. Okay, so once we have set that one, we also need to set the AD max. Now with AD max, we have to think about the refs. So we said we are going to use internal refs. So internal ref is 1, 1. Then Adler, so as we are using 8-bit, we can just do a left justified. So in order to have left justified, we just need to set that bit to be 1. Okay. Then we have got max 4 down to 0. We can use actually any of those. I can just say the first one, channel 0. Okay. So we can use just channel 0 over here, so that will be set. So in this case, AD max, it's going to be 0 hex E0. Okay, so we have got the second register configuration. Then we just need to enable the, we just need to start the conversion and check for the flag. So let's write the code for it, and let's see how it is going to work. So you just need to have the include file dot include and that will be m128 def.inc. So LDI, let's start with port D, so R16 0 hex FF, and that will be make port D output. then out DDRD R16, then port F to be an input, LDI R16 0 hex 00, make port F an input, so out DDRF R16. So the ports are set. Now we can set ADC SRA register LDI R16 0 hex 87, which we already calculated that, which will be enable ADC and select prescaler 128, which will give us 125 kilohertz ADC clock. So then that's all we need to do. So out ADC SRA R16. Then we just need to do the similar thing for the AD max, and that's going to be 0 hex E0 as we have found out, and that will be 2.56 VREF ADC channel 0 single-ended. So out AD max R16 and left justified. Let's not forget that. This is the configuration that we have got. So we have set the ADC, we have set the ports, and we are just ready now. So what we need to do is we just need to set bit of AD CSRA, which bit we are going to set is the AD SC bit. So we can say start conversion. So this will actually start the conversion. Now we have to check the ADIF flag as a polling. So SBIS, ADC, SRA, ADIF. So we have to check if it's the end of the conversion. So is it end of conversion, let's say. Now if it is no, then it has to jump back L1. Let's say this is L1. Keep checking. And if it is yes, it's end of the conversion. We have to set the flag, which we are clearing it actually. ADC SRA. So ADIF, and that's going to be clear ADIF flag. So then we have to read the data in some of the GPR. In R16, we are just less justified. We are just going to read 8-bit ADCH. So read only ADCH for 8 MSB result. Then once we read it, we have to send it to port D, and we have to output the value. Then we just need to repeat this, our jump L2, where it has to jump here to do another conversion. And we just need to repeat this. So this is a simple program that will do all of these for us. And once we've done the configuration of the register, rest is just putting all those together and starting the conversion, checking if it is the end of the conversion, if it's not repeat, and then when it is end of the conversion, get the data and send it out to port T. So this is the first example, part B, which is the assembly code. And this is also given over here. By polling, we just need to configure everything. And if you are using an interrupt, you just need to enable the interrupt and the IDF will be set automatically. You don't need to check anything else. So the C code, it's similar to assembly. Port T to be an output, port F to be an input, hex 87 for the ADSRA, E0 for ADMAX. We check the flag, start the conversion, check the flag, and then we clear the flag and we send the value to port T. That's all you need to do. So if we want, we can also use interrupts. We can also configure it to use interrupts. We just need to make few modifications to our code because we have to use ADC conversion complete, which is address 2A. So over here, we can just modify this to use interrupts. We can say dot csec rjump main, then we will have the address, so 002A is the ADC interrupt address, or maybe we can just use $sign for the address. Okay, and then we forgot .org. And then it has to jump to the interrupt, which is ADC ISR, let's say. And then somewhere after, let's use 100, we'll have the main. So the main code is here. As we are using interrupts, we have to initialize the stack. I'm just calling a macro. And then we have to enable the global interrupts. Now, few things that we need to change is on the registers. So in ADCS array, we have to set bit 3. Okay, so that bit is going to be 1 as well. And that will change to from 8.7 to 8F because these are all 1s now. So that will be F, enable ADC, enable interrupt. So we enable the interrupt and it's again going to be a single-ended. So ADMAX reference are still the same. Nothing is changed over there. So 110, 11, and then ADLA R is 1. And you can have it the left justified or the right justified. It's up to you. It's going to be the same thing. You just need to make the configuration accordingly. Okay, so I'll just keep it as E0, left justified. So what else do we need to do is, and we just need to wait. So we don't need anything else over here. We just need to start the conversion. Okay. and we just need to wait. So start conversion and then R jump wait. So that wait will be here. Now we are holding over there until the conversion is done. So here we can say ADC ISR, and we can just check, get the value for our IADC H. Okay, so read ADCH. Oh, I think it's converted to 10-bit digital. Channel 0 10-bit digital. So if it's we just need to make few modification. That means it's not going to be so it's going to be a 10-bit. We can have ADCH and ADCL both has to be read. So we have to read ADCL first, then read ADCL, then out port D R16. So we can say send low byte to port D. Then we read the high byte in R16 ADCH, read ADCH, and out port D R16. So send high byte to port D. And then SPI, we have to start the conversion again because when we get out from the interrupt, it has to carry on looking for a conversion. That's why we have to set it in the ISR, start conversion again, and then return from interrupt. So we can use interrupts and we can generate the ISR based on it. Okay, so only difference between that one and that one, this is right justified. So the only difference is this is C0. I've just done it with left justified, which is E0. That's the only difference. And now the rest is just the same. So interrupt handling and the rest are all doing together. Okay, so that's actually the end of this chapter. So we have seen how analog to digital and digital to analog converters works in principle, and their calculations, resolution spans, and the ranges. And we also seen how we can configure AVR in order to perform these analog to digital conversions. Thank you.